Okay, well, it looks like no one's coming. It's already time for class to start and they're not here. So let me go ahead and begin, and I'll just treat it as if someone is here. My students need this material, so I'm going to go ahead. Let me go ahead and start by sharing my iPhone/iPad screen. I'm having a hard time getting it to share, but it's coming, don't worry. So in this problem, we're asked to consider two conducting concentric spherical shells. Basically, you have an inner spherical shell that has an outer radius of r sub a and a total charge of negative u uniformly, or excuse me, negative q uniformly distributed over that outer surface. And then outside of that is another spherical shell, the inner radius of which is r sub b, and on that inner surface is a total charge positive q uniformly distributed all over that inner surface. And our job is to use the three-step process to compute the actual capacitance of the spherical capacitor. We're going to use step one, Gauss's law. You could also use Coulomb's law, but Gauss's law is much easier when the symmetry is good enough so that you can use it to extract the electric field out of the integrand. So we're going to use that. And then step two, we're going to use delta V equals the negative integral at E dot dl to compute the actual voltage difference between the negative Q surface and the positive Q surface. And if I actually integrate it from negative Q to positive Q, it should come out to be a positive voltage. And then step three, we're going to use C equals Q over V to compute the actual capacitance. And of course, I've mentioned to you several times before that when you do that C equals Q over V, the Q that's in the C equals Q over V should ultimately be canceled out with whatever contrivance of Q you have in the numerator of the volume of the voltage formula, because at the end the capacitance should always be a geometric quantity. It should depend on things like area and distances, but it should not have anything like lambda, the linear charge density, sigma, the surface charge density, or rho, the volume charge density. It shouldn't have those or Q's in it at all. So let me start by drawing the spheres and Gaussian surface and all that good stuff. So we'll begin as follows. Let's start off with solution. So this is our solution. We're going to make use of the fact that the closed integral of E dot dA is equal to Q enclosed over epsilon naught. We're going to make use of the fact that delta V, which is VB minus VA, meaning final minus initial, is equal to the negative integral of E dot dL. And we're going to make use of the fact that C is equal to Q over V. The biggest problem my students so far are having is realizing that Q enclosed and Q in general is either equal to the integral of lambda times dl, or the integral of sigma times the differential area, or the integral of rho times the differential volume. And if the charge is uniform, then we get Q is equal to lambda times L, or sigma times area, or rho times volume. So I just want to point that out again. Let's go ahead and draw us a coordinate system that we can make use of for concentric spheres. I'm going to draw the z-axis like that. I'm going to draw the y-axis like that. I'm going to draw the x-axis like that. Now I'm going to take out the handicap helping drawing thing, the little button that makes all my drawings look like straight lines or perfect spheres. And what I'm going to do is I'm going to draw a inner spherical shell, and that inner sphere is going to be centered on the origin. That actually was not bad, but I wanted it to automatically correct it and make it a perfect circle. It did not do that, so I redrew it. So that's the inner radius of the inner spherical shell. Now I'm going to draw another spherical shell, and that's the outer radius. So that's the one whose radius we'll call R sub A. Well, let's do R sub A. And now we'll draw a outer spherical shell. First, we'll draw the inner radius of the outer spherical shell. And that should look like this. Oops. I gotta remember to go here, and then 3 over, and then 3 down, and then 3 over again. So if I can use that, it should allow me to draw a fairly neat circle. Again, oh crap, I have it off the cool tool to make my drawings better. Okay, that's pretty good. We'll just ignore those dots. Now I'm going to draw the outer the outer radius of the outer spherical shell. This time I will go at half a mark, half a mark, half a mark, and half a mark, again using the feature of my note-taking tool to try to draw it as good as I can. Hopefully this will work. Not too bad, that's good enough anyways. I would in general try to slide it over a little bit if I can. Let's see if I can. Yeah, that's not bad. Okay, so that one's going to have an inner radius of RB. Like that. Now, what we need to do is we actually need a Gaussian surface between the inner charge surface, which is negative Q, and the outer charge surface, which is positive Q. To indicate those charges, I'm going to point an arrow right here and say this is positive Q. And I'm going to point an arrow right here and say this is negative Q. And now I'm going to draw a spherical Gaussian surface. So for my spherical Gaussian surface, I'm going to choose this really nice purple pillar. So I'm also going to take it at, let's say, 2¼ blocks. So it'll be a dot there, a dot there, a dot there, and a dot there. So now let's try to use my note-taking tool to draw the perfect sphere, which obviously you can see it's horribly drawn if I wasn't using that, but it's actually makes it harder to draw it when you're actually trying to hit specific marks. So that's why it turns out that way. So there's our Gaussian surface. Now I know this one, but generally speaking, when we do our Gaussian surface, we usually make the hypothesis first. And then the hypothesis allows us to construct a Gaussian surface on the surface of which either the electric field will work out to be 0, or it will work out, or excuse me, the electric field will work out to be a constant, and then that particular part of the left-hand side of Gauss's law will be E times A, or it'll actually be such that the electric field is perpendicular to the surface, in which case that part of the integral will be 0. So this one I skipped ahead because we've done enough spheres now that you probably realize that when you're doing a spherical charge distribution, you use a spherical Gaussian surface. But just in case, let's pretend like for a second that I haven't done the Gaussian surface and listen to my argument of how I choose what Gaussian surface it is. Okay, I am going to say that the radius of the Gaussian surface is just plain little r, like that. So what I'm going to do is state my hypothesis. So I'm going to go back to writing in green.
My hypothesis is, based on our knowledge of using Coulomb's law, I've figured out that
spherical charge distributions tend to make electric fields that are inversely proportional to the square of the distance from the center of the sphere to wherever you're at which you wish to know the electric field. So with that in mind, I'm going to assume that the electric field has the form E is equal to some E of R, meaning I don't think it depends on any variables other than the radial distance from the center of the sphere to the point at which we wish to know the electric field. And I'm also going to say that it points radially outward, and I'm going to do that by saying that this is E is equal to E of R times R hat, where R hat is the R hat from spherical coordinates. So this is from spherical coordinates. And what that means is you don't really need to know the details of how to compute, for instance, uh, the individual vector r hat, but you should know that it points radially outward. Sorry, I put my D so close to my eye, I couldn't make it out. So there's spherical coordinates. So basically what you do if you want to find out which direction the r hat vector points, you take any point in space and say you want to know the electric field there. Well, you draw a line from that point in space back to the origin, and then you trace that line from the origin back to the point, and that direction is the direction of r hat, except it's going to be exactly 1 unit long. Again, 1 unit, not 1 meter, not 1 Newton, not 1 Newton per Coulomb, but 1 unit. So it points radially outward. So that's how that's going to work. And because of that, we can see this hypothesis suggests that the magnitude of E only depends on the distance r from the center of the spherical distribution. We've put the distance, or we've put the center of the spherical distributions actually at the origin of the coordinates. So the r is actually the true r measured from spherical coordinates. So that also is somewhat helpful. But because of that, if we find a concentric sphere, in other words, a sphere who has the same center as our spherical charge distribution, then on the surface of that sphere, the electric field should be a constant. Therefore, we made a Gaussian surface that was a sphere, and since I needed to know the electric field between the inner conducting spherical shell and the outer conducting spherical shell, we only needed the Gaussian surface to be between RA and RB. So now we can begin with Gauss's law. And remember, Gauss's law is one of those weird equations that we have to work out the left side, we have to work out the right side, then we set the left side equal to the right side, and then we try to extract the electric field out of the integrand. That's one of the things we can do with Gauss's law, but we can only do it in these highly symmetric situations. And those are, of course, an infinitely large flat plane. We've done that, and in so doing, the Gaussian surface that we needed turned out to be a Gaussian pillbox, sort of like a soup can, where the lid and the bottom of the soup can are parallel to the plane, and the actual label part of the soup can actually penetrates through the flat plane perpendicular to the plane and goes all the way through to the other side to hit the bottom. When we do that, we find out that only the top and bottom give us a non-zero term on the left-hand side of Gauss's law. Another surface we can use, or another sphere distribution of charges that we can use with Gauss's law this way, is the infinitely long cylinder. And in that one, we also use a Gaussian pillbox or a soup can. But the weird thing here is the top and bottom of the soup can would be perpendicular to the actual wire. The wire would actually go right along the rotation axis of the cylinder. And it turns out that only the soup label portion is going to give us a non-zero integral on the left-hand side of Gauss's law, whereas the lid and the bottom are going to give us 0. So those are our three surfaces. Basically, you have infinite planar, which requires a Gaussian pillbox, only the top and bottom survive. We have an infinitely long wire or infinitely long cylinder. And again, we have a Gaussian pillbox. This time, the actual axis of the cylinder is parallel to the wire, and only the soup label gives a non-zero integral on the left-hand side of Gauss's law, or a spherically symmetric charge distribution, which requires a concentric sphere, and the whole surface becomes relevant.
So let us begin. I'm going to start off with the left-hand side. Oops, I was using green, so let me use green. Left-hand side of Gauss's law is the closed integral E dot dA. So this time we're lucky in that we're doing a sphere, and the sphere is not broke up into multiple pieces. So there's really just one integral here. And that integral is going to be E of R hat. That's from our hypothesis. And then we're going to dot that with our differential area element, which I've mentioned to you before, the various ways you could come up with a differential area element. But the whole point of using Gauss's law this way is that you never have to actually figure out what the integral parts are. You just have to spit out the integral answer, which is the electric field strength on the surface times the surface area. So in this case, we're just going to call the differential area element dA, and it also points in the r hat direction. In fact, if you wanted to think about the actual Gaussian sphere, the Gaussian spherical surface, it would look a little bit like this, and the a patch on it, the dA, might be a little bit like that, and the dA would point radially outward, just like that. So that's really what we're looking at in terms of the Gaussian surface and the dA vector. So hopefully that's helpful to you. And notice, because it is pointing in the r hat direction, we're going to get a really nice integration here. So with this case, we know that we're integrating on the surface of the Gaussian sphere. So the r is actually fixed. It's specifically the radius of the sphere. And because of that, E of r is a constant. So we end up getting E of r falling out in front. And now we use the linearity of the dot product. And the linearity of the dot product allows us to pull all the non-vector parts all out in front of to the left side of the dot product and leave just the vector parts doing the dot product. So the scalar part I would have pulled by was E of r. Another scalar part I pulled by is dA. And then I'm left with just r hat dot r hat, which of course is 1 times the cosine of 0, which is 1. So ultimately what we get is the electric field E of r on the Gaussian surface of radius r times the surface area of the Gaussian surface of radius r, and the surface area for a sphere is 4 pi r squared. So that's our left-hand side. The right-hand side, on the other hand, the right-hand side of Gauss's law is Q enclosed over epsilon naught, and as we told you before, we can use Q equals the integral of lambda dL, or sigma times the integral of dA, or rho times the integral of dV. The surface of a Gaussian sphere is in fact a two-dimensional surface, so you should immediately start thinking that it's a sigma, because sigma is charge per unit area, so it'd be like coulombs per square meter, and the surface area is clearly a square meter, or measured in square meters. So we're thinking of using the sigma, and in fact what we have to figure out is the total charge inside of the Gaussian surface. We can see from the diagram that I drew a charge of negative Q on the outer surface of the inner shell, and that entire inner shell is inside the Gaussian surface. So I don't even have to do any of the sigmas or the lambdas or the rhos, because I have the total Q. If we were doing a regular problem where I had to calculate the electric field at points r less than RA and at points r greater than RB, then I might have to resort to using the lambda DL, the sigma DA, or the rho DV. So in this case, I'm just going to write Q as the charge enclosed. It's technically negative Q, but that doesn't matter. That would just tell us which direction it's going to point. And in fact, it's actually going to point radially inward. So I guess in principle, we could, in general, put a negative there and then put it over epsilon naught. And that would be the left-hand side, or excuse me, the right-hand side. Now we set the right-hand side equal to the left-hand side. Well, I should probably put the right-hand side on the right-hand side, so maybe it'd be nicer if I wrote that the other way. So I'll put left-hand side equals right-hand side. And what we get is E of R times 4 pi R squared is equal to negative Q over epsilon naught. And using our original hypothesis that E is equal to E of R times R hat, I can now say that the electric field E is in fact negative Q over 4 pi epsilon naught R squared R hat. And the negative just tells us specifically, hey, you've got a charge of negative Q on the inside, so the electric field will be pointing from the from the outside of the inner sphere towards the inside of the inner sphere. So from the radius RB towards the radius RA. And that is our completion of step one. I'm going to use blue to highlight it so we can make use of it. I wouldn't normally take off if you didn't put the negative there. This is in fact the first time I've ever drawn it, even though I think I've probably done it before and just ignored it. But anyways, it should technically be a negative. If anything, I'd take a half a point or something off that. But generally with the multiple choice type answers we have, that's not going to be an issue anyways. So we did just finish step one. So there's step one. Step two is we're supposed to use delta V equals V final minus V initial equals a negative integral of E dot dl. So that's what I'm going to do now. I'm going to say step two, delta V equals, let's see, V at, I'm going to go from the negative Q to the positive Q. So my final position is going to be R sub B. So I'll call that VB. And my initial position, ooh, this should be, that negative shouldn't be there. I was starting to write the integral already. So it would be V at R sub B minus V at R sub A. And that's equal to the negative integral of E dot dl, which we know is a path or line integral. So again, I'm going to say delta V, and this is where I use this actual problem to practice my skills at line and surface integrals, because I'm trying to set it up to go the right direction to get the right result, and therefore the voltage should come out to be positive. If I make a mistake on my line integral, then it might come out negative, or if I make a mistake about setting it up, it could come out negative. So I am attempting to integrate from the negative Q to the positive Q, because the negative Q is associated with the low voltage and the positive Q is associated with the high voltage. And if you do the voltage of the high one minus the voltage of the low one, you should get a positive quantity. So my electric field is actually going to point inward. It would be negative Q over 4 pi epsilon naught R squared in the denominator. R hat, that's the actual electric field. And I have to move from RB to RA. Now, what I'm going to do is I'm going to choose my DL to indicate which direction I'm going. The direction I'm going is from RB, or excuse me, from RA, which is the outer radius of the inner shell. And it's going to go to the inner radius of the outer shell, which is RB. So that is actually in the positive R hat direction. So I'm going to call DL positive DR and then R hat. So this indicates the direction. I could just put that by like here and say direction. And then once you decide which one's going to be the direction, the other one, which in this case would be the range of integration, that's just going to go from low coordinate to high coordinate, which in this case is from RA to RB. So it's the same thing either way. So I'm going to integrate from R sub A to R sub B like that. Now we go off in our normal process. Notice the two negatives are going to cancel one another out, and the Q over 4 pi epsilon naught is all a constant, so it can go out in front of the integral. So I'm going to get positive Q over 4 pi epsilon naught times the integral. All I've got left of the electric field is basically the R squared in the denominator. And I'm going to use the linearity of the dot product to pull the dr out to the left of the dot product. So I'm going to get r to the negative 2, r to the negative 2 times dr. And then we have r hat dot r hat again, which of course is just 1. Now the integral of r to the negative 2 is negative r to the negative 1. So now I'm going to get negative q over 4 pi epsilon naught r hat, or excuse me, r, and that's going to be evaluated from RA to RB. So when I do that, that's going to become negative q over 4 pi epsilon naught. Now it'll be 1 over RB minus 1 over RA. Now notice in this case, RB is the bigger number, so 1 over RB should be the smaller number, and 1 over RA would be the bigger number. So when I subtract 1 over RB minus 1 over RA, I'm going to get a negative number, which canceling out with the negative sign gives me a positive voltage, so I know I did it correctly. Just to get rid of the ugliness of the negative, though, I'm going to go ahead and reverse the order, and I'm going to say Q over 4 pi epsilon naught. And now I'm going to say, again, reversing these two, what's going to happen is I'm going to get 1. Ooh, that was bad. I just erased everything. I'm going to get 1 over RA minus 1 over RB. And then this sign is going to become positive. But to get a common denominator, I'm going to multiply this one by RA over RA. And to get a common denominator, I'm going to multiply this one by RB over RB, like that. So ultimately, what we're going to get is, I don't know why I switched to blue, but anyways, here we are, RB minus RA over RB. And that is equal to the voltage difference between the negative Q outer surface of the inner conducting sphere and the positive Q inner surface of the outer conducting sphere. So I'll box it off in green so we can easily point to it. And we've now completed step 2. Step 3, on the other hand, step 3 is using C equals Q over V to calculate the capacitance. I'll go back to green because that's what I was supposed to be using. So I'm going to say C is actually equal to Q divided by V. Now the V is Q over 4 pi epsilon naught, and then RB minus RA over RA times RB, like so. So ultimately, you can see that what happens is our capacitance, notice the Q's do cancel out. So I can show you that right now. That Q cancels out with that Q. This 4 pi epsilon naught is in the denominator of the denominator, so that's going to become the numerator. And RA and RB are also in the denominator of the denominator. So this is going to become 4 pi epsilon naught RA RB divided by RB minus RA, and that is the capacitance formula for a concentric spherical shells. Since there's nobody here, I'm not necessarily going to ask anyone, do they have questions, but this is the paradigm that I've been talking about. Step 1, using usually Gauss's law, but you could use Coulomb's law to find the electric field between the negatively charged portion of the capacitor and the positively charged portion. Then step 2 is to use delta V equals the negative integral at E dot dl to calculate the voltage difference between the negative Q part and the positive Q part. And I recommend you go from the negative Q to the positive Q so that you get a positive voltage, because you ultimately need to divide by a positive voltage. And then you use step 3, C equals Q over V, to find the ultimate capacitance. And that's what we've done here. So hopefully everybody follows that.
And if you look in your book has a very similar example. This one's similar to example 24.3.
So I'll just say like example 24-3. And when you look at 24-3, they probably, I think they do use lowercase r's or something weird like that. But if you look at it, it's more or less the same type of problem. And we have a very limited number of problems, so I can't imagine this is a copyright violation. But the main thing is you'll see that my answer, once you make the change of the variables to match their variables, my answer is the same as their answer. So
we'll go on. There's another example, and this will be really the last one of where we're going to calculate the capacitance of a wire situation. In this case, we actually have two parallel wires of very small radius running right parallel to each other. The only time I've seen wires like this is back when I was a kid and TVs had on top of them big circular antennas or some other weird type of antennas, but they'd have a wire running from the back of the TV to that circular antenna, and then the circular antenna you could turn excuse me, you could turn a knob on it and it would take that circular antenna and it would turn in different directions like this, and you actually had to aim it at in the direction of the station putting out the TV channel that you were watching, and that's how you'd pick up the TV station unless you were so close that it didn't matter. I always lived I always lived fairly close. I was in Portsmouth, and the stations were mostly in Norfolk, and there was one like in the border of Portsmouth and Suffolk. So they were fairly close, but we spent a lot of our time in North Carolina, and they didn't have a radio TV station anywhere near the Outer Banks of North Carolina. So we had to pick up the ones from Virginia, and it was very obvious that you had to point it that way. The sad part is we chose in America to vertically polarize our electromagnetic radiation that we send out, for instance, from radio stations and television stations and stuff like that. And because of vertical polarization, we actually have to have our antennas aligned uh, in the direction of the polarization. Whereas if we'd done it negative, or if we'd done it horizontally polarized, then basically the antenna would have matched no matter what direction we came into. So that's kind of a bummer. But anyways, let me show you the actual diagram of the next setup we're going to do. So in this one, again, I am going to show you what we have. I'm going to draw one of the wires as a small circle, and I'm going to draw the other wire as a small circle as well. And this wire on the left, I'm going to say that one has a charge of negative Q. And this one on the right has a charge of positive Q. And it doesn't really matter where we draw our coordinate systems, but just for the heck of it, I'm going to draw a coordinate system that has a y-axis right through the center of the negative Q. Well, that was goofy. So that's my y-axis. I don't know why it wants to continue pushing it to the side like that. I'm trying to draw it vertically, but it's being a pain. Okay, so that's my y-axis. And then my x-axis is going to go right through the middle of the other charge like so. And now I'll draw my y-axis and I'll draw my x-axis like that, label them. You can see that the negative Q is in fact centered on the origin, and the positive Q is actually going to be centered on a distance D. So what I'm going to do is, in this coordinate system, I'm going to draw a line right at the center, and I'm going to say that distance is D. And I'm going to further tell everybody that this distance from here to here is actually 2r, which means the radius of that wire is in fact r. I'm going to do the same thing over here. These two wires are going to have the same radius, and that radius is capital R. Now, in this part, we would normally start off with drawing a Gaussian surface for one of them, and then compute the electric field due to that one. And then, because they're sort of the same thing, one just has negative charge on it, and the other one has positive charge on it. Because of that, uh, we would normally do Gauss's law for one infinitely long cylinder because these are supposed to be wires that are infinitely long going into the board or into the screen here. And we've actually already done that. We know specifically because we did it with Coulomb's law, and we got that the electric field always pointed radially away, but radially with only X and Y components. We actually imagine the axis of the rotation axis of symmetry, if you will, of the actual wire. We imagine that along the Z axis, and then the X and Y axes were perpendicular to it. So if you measured a distance that was either parallel to the x-axis, parallel to the y-axis, or parallel to the xy plane, that distance would be r, which we recognize as the cylindrical coordinates r. And we got that the electric field was lambda, the charge per unit length, over 2 pi epsilon naught r. So we're just going to use that result and bypass step one because it's more important for us to just figure out how to do the actual calculation for this one. So what we do know is, and actually I should probably state what the problem is too, is say, let's say compute / derive the capacitance of this device. And I say device, but it's really just a wire. They do sell these wires still. I've seen them at Home Depot and Lowe's and stuff like that. But again, just remember we're imagining these black circles as infinitely long cylinders going into the page and coming out of the page. Okay. Now the solution is, in this case, I think I'll use purple for my solution. I'm going to say solution. And this is where you state what equations you plan on using. I don't have to use Gauss's law here, but I am going to use the fact that the electric field due to a cylinder of charge, an infinitely long cylinder, is lambda over 2 pi epsilon naught. And I should probably take a little bit of time to remind you guys that lambda is charge per unit length. So you could also write this as E is equal to Q over 2 pi epsilon naught L, where L is the length of the wire that you're considering at that particular point in time. Obviously, for an infinitely long one, it would be infinity, and that doesn't make any sense. But you can actually bite off chunks of it, and as long as you're not near the end, that's close enough. So that's 2 pi epsilon naught L, and then R like that. We're also going to make use of the fact that delta V is equal to the negative integral of E dot dl, and we're going to make use of the fact that C is equal to Q over V. Okay, so that's what we're using. So I'm going to start off by realizing that the negative Q in principle is going to have a electric field that's centered on the origin. What that means is the electric field between the two is actually pointing this way due to the negative charge. So that's E due to the negative Q. It's pointing that way. Of course, it's also pointing this way. It's also pointing this way. It's also pointing this way, so on and so forth. But the main thing is it's that, and it's given by the formula I just wrote, and we'll call the distance from here to, let's say, here, we'll call that distance just x. And the reason why I do that is because this formula R, or this formula for the electric field, is in terms of R, and R is the distance from the center of the wire to the point at which we wish to know the electric field. So in the case of the positive charge, this distance is relevant if we wish to know the electric field here, and this distance would be listed as d minus x. Okay, but what we notice here is the positive charge is creating a electric field that points this way, and that's E due to the positive Q. The main thing being that between these two charges, between these two charged wires, the electric fields point exactly the same way. So they just add. You don't have to have one negative and one positive. And in fact, they're going to point in the negative I hat direction. So we can go ahead and start with step two.
So I'm going to start with step 2. So here's step 2. Delta V equals V. Let's say we're going to go from the negative charge, which is at the origin, to the positive charge. So I'm going to say V of positive Q minus V at negative Q. That's the direction I'm going because that'll give me a positive quantity. That's equal to the negative integral of E dot dl. What my electric field is going to be is first the electric field due to the positive charge. So let me write it here, E total. And I don't need to put a vector here because we know everything's along the x-axis. So I'll just say E total is equal to E negative plus E positive. And it's just purely plus because they're both pointing in the same directions. So for the negative case, we're going to get Q over 2 pi epsilon naught L. That's going to be true for both of them. So I'm just going to factor that out. And for the negative charge, the distance will be x. So I'm going to write it as 1 over x. And for the positive charge, the distance is going to be d minus x. So I'm going to write 1 over d minus x there. And then I know the electric field will actually point in the negative direction. So I'm going to put a negative sign there. And I'm going to put an I hat here. And I'm going to dot that with, again, using my dl vector to indicate the direction of integration. I can write out the dl now, but first I need to move my formula for E total because it's obviously in the way. So let me see if I can move this over to here or something. Let's say cut, and I'll say paste. So I don't think that's too terribly bad. That should give me enough room. So now I'm going to use my DL to indicate the actual direction we're integrating. We are integrating from the negative Q to the positive Q, so that's actually in the positive I hat direction. So I'm going to write dx, whoa, I'm going to write with the actual marker, that'd help. So I'm going to write dx I hat, and that shows that I'm integrating to the right, which is in fact from the negative Q, which is a low voltage, to the positive Q, which is the high voltage. Since I've done that, now I've got to write my integration limits. I'm going to go from the small coordinate to the large coordinate. And of course, we have to go all the way from nearly 0, specifically a distance r away from 0, all the way to d minus r. The smallest, of course, would be just plain 0 minus r, or excuse me, 0 plus r. So we'll just call that r. And the other one's going to be a distance d minus r. So that's what our actual integration has to be. Notice the two negatives cancel out, and I can pull the q over 2 pi epsilon naught L out in front. That's going to give me q over 2 pi epsilon naught L. That's all going to be in front. And now I'm going to use a curly bracket so I can break this up into two separate integrals. I'm going to use the integral from r to d minus r. And that is going, yeah, that makes sense. I'm just making sure I'm going the right direction. I did this earlier and went the wrong direction and ended up getting a negative by mistake. But what we have now is 1 over x dx, and then I hat dot I hat like this, which of course is 1. And then we have the next integral, which would be plus integral, again, from r to d minus r. And in this case, it's going to be dx over d minus x. And that would be times I hat dot I hat, which again is just 1. And now I can close my curly brackets like so. Now, what I'm going to do for this one is I'm going to say, actually, let's do this a little neater so y'all can see what I'm writing here. Whoa, that was supposed to be a erase mark, but it did not erase. Okay, so I'm going to say let u equal d minus x, which implies du would equal negative dx. So I need a negative to go in front of the dx. In order to do that, I need to multiply by another negative. So this is going to become negative here. And then this whole thing is going to become u. So now we've got our substitution. We can do our integral. We already know what the integral of dx is, or excuse me, the integral of dx over x is. So I've got q over 2 pi epsilon naught L times, here's my curly bracket, the integral of dx over x is just ln, and that means I take the natural log of x and I evaluated at d minus r, and then I subtract from that the natural log evaluated, or the natural log of x evaluated at r. But when you write the ln of a minus the ln of b, that's the same thing as the ln of a over b. So I'm going to write this as the natural log of d minus r over r. So that's for the first integral. Now I have a minus sign from where we did the change of variables here. And we have the integral of du over u. That just gives me, again, the natural log of u, and u is d minus x. And we're going to evaluate d minus x at d minus r. So that's literally going to become d minus r over just plain r. And you can see when you do d minus r with the d minus r in parentheses, the negative has to be distributed, so the d minus d becomes just 0, but we're left with a positive r. So we can do d minus d plus r, which is just r over r, and that's it. So in this case, that does look right. Let's see. I am integrating from r, right? And I'm integrating up to d minus r. That's right. So that all looks good to me. Yes. And another thing you might notice is d in general should be way bigger than r. If you've actually ever seen these wires, you'll notice the wires are very small on the two sides, and it's got this hard sort of clear plastic holding them together. And that clear plastic part that connects the two wires is usually more than a centimeter wide, or around a centimeter wide, whereas the wire has got like a millimeter type diameter. So that's about a factor of 10. We can relate these two natural logs first by taking d minus r and just calling it approximately d. And the other thing, when we have this, we have ln of d minus x. Oh, this would be, the bottom's not just plain r, the bottom's d minus r. Sorry about that. Let me fix this real quick. That's why I was hemming and hawing. I was trying to figure out what I did wrong. The integrand was d minus x, so d minus x becomes d minus r. That looks better. Okay, so I have that. Now I can compute a little bit farther. I'm going to say q over 2 pi epsilon naught L times, now the natural log, or the difference of natural logs, is the same thing as division of the arguments of the log. So the log of a minus the log of b is the same thing as the log of a over b. So in this case, I'm going to say the natural log of d minus r over r divided by, remember, d minus r just becomes r, and then this becomes d minus r down there. So what you can see is when you divide by a fraction, that's the same thing as multiplying by the reciprocal of the fraction. So if I take that bottom fraction, which is r over d minus r, I have to flip that over. That's going to become d minus r over r. So I end up getting q over 2 pi epsilon naught L times the natural log of d minus r squared over r squared. But another property, I should probably write them down. Let me write a couple of them down. The ln of a plus the ln of b is equal to the ln of a times b. The ln, the ln of a minus the ln of b is equal to the ln of a over b. and the ln of x to the y is equal to y times the ln of x. That's the principles I've used, and this is true for all logarithms, not just lens. And in fact, sometimes if you use the base, you can get real nice simplification. So instead of just using x down there, I could have used a e for my base, and of course the ln of e is just 1. So with this in mind, I can cancel out the actual 2 that I have here and here will cancel out with the 2 that I have here, because it's really going to pull out in front. Not only that, d minus r is really, really close to just d. So I'm going to make that simplification, and finally I get delta v is equal to q over pi epsilon naught L times the natural log of d over r, like that. So I'll box this off so we can easily find it for step 3. We're now finished with step 2. So step 3 is straightforward enough. Step 3 is using C equals Q over V. Luckily, this has the Q right in the V formula already, so I'm just going to put the Q on top, and then I'm going to do Q over 2 pi epsilon naught L times the natural log of D over R. Now, in this case, the Q's do cancel out. You can see that Q cancels out with that Q. The 2 pi epsilon naught times L goes to the numerator, but to be honest with you, we rarely talk about the total capacitance. We normally say the capacitance per unit length when we're talking about wires like coaxial wires or this antenna wire that I'm referring to here. So I'll go ahead and show it that way. I'm going to say C over L, which is the capacitance per unit length. That would be measured like in microfarads per meter or something like that. That is in fact going to equal 2 pi epsilon naught over the natural log of D over R, where D is the distance between the centers of the actual wires and R is the radius of the actual wires. And now we're done. Again, this example is very much like the other example in your book, which was, I think, example 24-4. So I'm just going to write that here so you'll remember, so you can look it up. This is like example 24-4. Okay, so hopefully that helps you. Now that's the last example that your book. Oh, I actually said we were going to cancel out the 2, and I canceled out the 2, but I left it. I put it back in here in step 3. So let me fix that, everybody. Please notice this. I canceled out the 2, but then I forgot to cancel out the 2. So I'll put that back in here. I got to get the right color so I can fix my pi. There's my pi. And I can also get rid of this 2 here, because remember we did cancel it out. So now I get pi epsilon 0 over ln d minus the d over r. That's the actual formula, and I apologize for screwing that up for a second. Again, I would normally ask for questions, but there's nobody in class today, so I'm going to just press on. The next section in our book that we're covering is capacitors in series and parallel. And sometimes I choose to skip the derivation and just give you the formula. But to be honest with you, I figure the formula and deriving the formula for series and parallel capacitances is very instructive in teaching you exactly how capacitors behave in circuits with batteries. So I'm going to go ahead and do that now. So let's start another section. We're going to say calculate the capacitant, or the equivalent capacitance equivalent capacitance of multiple capacitors A in series and B in parallel. So that's our actual problem that we're to solve. So I'm going to start off with capacitors in series. What I'm going to do is I'll draw a circuit as if this is a battery. I'm going to use a V with a subscript so I don't get confused for the general term for voltage. So the voltage of this battery is V0. A wire comes out of the positive side of the battery, which is this side, and this is the negative side of the battery. That's important to keep your wits about you here. And then the wire turns and we go over to here and we run into our first capacitor, which is going to have a capacitance C1. And then our second capacitor, which is going to have a capacitance C2. And then our capacitance C3. And that's enough. Actually, we could have done it with just two, but we'll see the generalization is quite natural for any number of capacitances, but that's what they look like in series. Okay, so this is their capacitor in series. I'm just going to say solution. And this is part A, and what I'm using in the solution is just C equals Q over V, which is pretty much all we need. Now, remember, if you say the voltage of the battery, let's say is 12 volts, then the voltage across C1 plus the voltage across C2 plus the voltage across C3, since they're all in series, must add up to give you the voltage across the battery. So that's another principle that we need. So due to being in series, V0 is equal to V1 plus V2 plus V3. Okay. Of course, if we had n of them, it'd be V1 plus V2 plus V3 plus dot, dot, dot on up to Vn, and you'd see where we generalize it to. Now, we also know that from C equals Q over V, V has got to equal Q over C, so we'll make use of that as well. But here's where I've got to explain what happens. So when I say I want an equivalent capacitance, what I mean by that is I'd like to find one capacitor that I could put in this circuit with this battery, and the battery wouldn't know any different. So the equivalent circuit would look like this, basically, where you have C equivalent, and I'll put an S on it for series, and then it goes back like this. So that's the equivalent circuit, and that's the equivalent capacitance. And in fact, that will be referred to so that we can find out stuff about the V0 on the left-hand side of that equation that I just wrote. And I'm going to call that equation 1, by the way. And I should probably write it in purple. So this is equation 1. So what we have to realize is going to happen is a certain amount of charge is going to leave the battery. The reason why is the positive charge on the side of the battery. Remember, the positive side of the battery looks sort of like a positive charge. It literally looks like the positive side of capacitor. And because of that, it's positively charged. So the wire that's made of a conductor, and conductors being that it's a material in which there's free electrons able to move around the material. We didn't necessarily know it was free electrons. We just knew there were free charges. And as luck would have it, we guessed wrongly. But now we still pretend like it's reality. So we're going to pretend like these loose positive charges are going to run to the left away from that positive terminal of the battery. And they can't go very far, of course, because they're going to run into an open circuit, because that's what a capacitor is. It's literally a hole in the circuit where there's an air gap between one part of the wire and then the next part. So what's going to happen is we're going to build up a charge on the first capacitor, and it's going to be positive, and then positive, and then positive, and then positive. And in fact, every bit of charge Q0 that leaves the battery has to come to the capacitance C1. So we know not only that C1 has the left-hand side positive, but we also know that the charge on the left-hand side is positive Q0. Okay. Now this positive Q0 is going to compel all the free positive charges in the right-hand side to move to the right. They're going to flee the positive side, and that's going to leave the right-hand side negative. And this is in fact going to cause a charge of negative Q0 on this side. The original wire was, of course, probably neutral, meaning it had no charge whatsoever. So now, to make up for the negative Q0, it's going to make a charge of positive Q0 on this side. And of course, that's going to do the same thing to the right-hand side. So we're going to get a negative Q0 here. And again, we're going to get a positive Q0 on this side and a negative Q0 on this side. And that's ultimately what's going to happen. Now that last positive Q0 on the left-hand side of C3 is going to compel the positive charges in the right-hand side of C3 to run away. And not only that, they're going to be attracted to the negative end of the battery because that looks like a negative charge plate. So that discussion I just had was basically telling you how charges are going to behave when you connect three capacitors in series to a battery. So what we now see is that V equals Q over C. What we know is V is actually going to generate a charge Q0, and that voltage V0 should be equal to Q0 over C equivalent S. So I'm going to say from equation 1, I'm going to have Q0 over C equivalent S, because that represents the end circuit where we have one capacitance representing it. The right-hand side of equation 1, however, is going to have Q1, the charge on the capacitance C1, divided by C1, plus V2 would be Q2 over C2, and V3 would be Q3 over C3. But what we learned from that description of what would happen is that there we go, erasing again. What we learned from that description is that Q1 is equal to Q2 is equal to Q3 is equal to just Q0. Because of that, we can basically convert all of these Q's to Q0 and then divide both sides by Q0. And what we're left with is 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And just like I said before, we could have plus V4 plus V5 on up to Vn. So I can just say plus dot, 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 and that is the full derivation of the equivalent capacitance for capacitances in series. You might notice from your experience in lab that resistors in parallel had the same formula, but they were in parallel, whereas these capacitors are in series. So resistors in parallel have the same formula. 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So that's kind of nice to at least get another formula that you already knew, except it's in a different guise with different symbols. Okay. Now we're going to do part B. And we still have quite a bit of time left at 6:25. Class runs till 7:40, or excuse me, 6:40. So we still got about 15 minutes left. Now I'm going to do part B. So with part B, what we're going to have is, again, a battery whose voltage is V0. It has a positive and a negative side. The wire is going to come out of the battery. It's going to run up, and then it will have a capacitance C1, and then there will be another capacitance C2, and then just for completeness, we'll do 3. Again, we can extend this to N like I suggested we do before, and it would all work out just fine. And we're going to generalize it when we're done anyways. But basically, what we have now is a circuit whose we want to make the equivalent of, and the equivalent of course, would be V0, positive, negative. One wire goes around to one capacitor, and that capacitor would be C equivalent with a subscript P for parallel. So that's what we're ultimately shooting for, is the equivalent circuit, which is that bottom one. But again, we're going to make the assumption that a total charge Q0 is coming out of the positive side of the battery. Again, it's not necessarily coming out, it's more like the positive voltage of the positive terminal of the battery acts like a positive charge, and it compels all the positive charges that are free to move in the wire to run around away from it. So the Q0 is going to run away from the positive terminal of the battery, and it's going to get to this junction right here, and some fraction of the Q0 is going to go this way, and I'm going to call that Q1. And then the rest of Q0 is going to go up and it's going to run into this junction. Some fraction of them, let's call it Q2, is going to go that way. And then what's remaining will be Q3. And that's going to go to capacitance 3. Now, what you can see is obviously I'm going to get a positive charge on the left-hand side of each of the capacitors like this. That's going to compel a negative charge to build on the right-hand side like that. And then that's going to compel the same charge Q0 to come back to the battery as a closed circuit as we expect. And in fact, we're going to know that based on conservation of a charge, we have equation 1, Q0 is equal to Q1 plus Q2 plus Q3. Of course, if we had 4 or 5 or n capacitors, it'd be plus Q1 plus Q2 plus dot 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 on up to Qn. That's how we would generalize it. We also know that C equals Q over V, which is sort of equation 2. Well, actually, I won't call it equation 2. I'm going to solve that for Q, and we'll see Q is equal to CV, and I'll call that equation 2. Now I can combine equation 2 and equation 1, and I'm also going to use the drawing from the second circuit down here where I have Q0, and this is positive Q0 over here and negative Q0 over here. Notice the capacitance always has an equal charge on each side of the capacitor, but one's positive, the other one's negative. So for the Q0, we can compare it to the circuit down below, which we're going to say is C equivalent parallel times V0. And then Q1 is going to be C1 V1, and Q2 is going to be C2 V2, and Q3 is going to be C3 V3. Of course, again, if we had more, we just have more terms. Now, one thing we did learn from our labs as well is that when you have a battery and 3 capacitors all in parallel with each other, then the voltage of the battery is the same as the voltage on the first capacitor, and it's the same as the voltage on the second capacitor, and the same as the voltage on the third capacitor. So we can also use equation 3, which is V0 is equal to V1 is equal to V2 is equal to V3 equals dot dot dot. Again, that's for extending it more than 3 capacitors. So what we can do is convert all these V's to V0. So I'd have C equivalent V0 is equal to C1 V0 plus C2 V0 plus C3 V0. And finally, that gives us C equivalent parallel is equal to C1 plus C2 plus C3 plus dot dot dot, and that allows the extension to any number of capacitors in. So that's it. That is actually the derivation for the formula for the equivalent capacitance in series, or in parallel in this case, and the other one was the one for series. So again, notice that's another formula that we already knew. Specifically, we knew that formula for resistances in series, but now it happens to be applying to capacitors, but the capacitors are in parallel. So again, I would normally like to ask questions and get you guys to ask me questions if you have any, but now instead I'm going to go ahead and do a fairly simple example. I'm going to make it less simple than the book's example, and this is sort of like example 24.5. Let's make a circuit, and we're going to
compute what the equivalent capacitance of the circuit is, and then I'm going to compute what the voltage is across each capacitor and what the charge is on each capacitor. So this is sort of a combination of two examples in your book. I'm going to call it just a plain example. So find the equivalent capacitance of the configuration below and then compute the charge and voltage on each capacitor. Okay, so my circuit's going to look like this. I'm going to have a battery, the positive side, the negative side, and I'm going to say, let's say V0 is equal to 6.00 volts. And now I'm going to allow this circuit to come up here, and now it's going to turn and it's going to break up into a pair of parallel capacitors. I'm going to call this one C1. I'm going to call this one C2. And then those wires are going to come back together, and there's going to be another capacitance here, and that's going to be called C3. And then this wire will return back to the battery on the negative side. And I'm going to say C1 is equal to, let's say C1 is 4.00 microfarads. Let's say C2 is 8.00 microfarads. And let's say C3 is, let's say 12.0 microfarads. Okay. So now we're going to work the problem. Solution. What we're going to use is our formulas. 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus ... And C equivalent parallel is equal to C1 plus C2 plus ... And we'll go on from there. One thing I want to mention, though, the formula for capacitances in series, that's a neat little construct where basically the equivalent capacitance of any number of capacitors other than one is smaller than the capacitance of the smallest capacitance in the series. So that's kind of interesting. And then, of course, the other one's just the sum. So when I go to reduce a circuit like this to equivalent capacitance, I look for any two or more capacitance that fit the description. Are any two specific capacitors in series, meaning exactly in series, or are two or more capacitors in parallel, meaning exactly in parallel? Like you can say that C2 and C3 in some sense are in series, but they're really not, because C2 is actually in parallel with C3, and then C1 is, or excuse me, C2 is actually in parallel with C1, and C3 is actually in series with that parallel band of resistors or of capacitors. So that's why C2 and C3 are not really in series yet. But C1 and C2 are. So I'm going to take the two C1 and C2, which are in parallel, and I'm going to compute the equivalent capacitance of that, and I'm going to call it C2 So C12, it means the capacitance, the equivalent capacitance of capacitance 2 and capacitance 1, they're in parallel, and that means that it should be equal to C1 plus C2, which of course is equal to 4.00 microfarads plus 8.00 microfarads, which equals
12.00 microfarads. So we now have a circuit that we can rewrite as battery capacitance C12 in series with capacitance C3, like that. And again, this is just plain V0 equals 6.00 volts. Now I have C12 and C3 are in series, so I can use the formula there. That'll finish up all of them. So I'm just going to call that one C equivalent. So they're in series, so I know 1 over C equivalent. Again, I'm just calling it C equivalent because it's going to be the final answer for well, for what I'm assuming is part A. That's equal to 1 over C12 plus 1 over C3. 1 over C12 is 1 over 12.00. I'll leave the units off. And 1 over C3 is 1 over 12.0. Probably wouldn't hurt to go ahead and put another 0 on there as a sig fig. So notice now that C3 has 4 sig figs just for the heck of it. So now I'll go back and put a fourth sig fig on there as well. Obviously, the least common denominator is 12, and it's already in that form. I didn't choose that on purpose. I just got lucky. So this is going to be 2.00. That actually would go to any number of decimal places over 12.00. And of course, that means C equivalent is 1 over 2.00 to any number over 12.00. So that's basically 12 divided by 2, which is 6.000 microfarads. So now I can say that the equivalent circuit is, in fact, V0 equals 6.00 volts. And that is in series with a single capacitance of 6.000 microfarads, like that. So the equivalent capacitance of the entire bank is this. That's our answer sort of for part A. I didn't label it part A, but I will now. Now I want to realize that the C equals Q over V applies perfectly to this. C equals Q over V works perfectly for this one because I'm basically going to get a very specific amount of charge Q. That's going to be the Q that's coming out of the battery. So I'm going to actually call that Q0. So I'm going to say Q0 over V0. That's going to give me that for part B. I should be writing in blue again. Let me do this. So writing in blue again, I'm going to say for part B, Q0 is actually equal to C equivalent times V0, which is 6.000 microfarads times 6.00 volts. And a coulomb, or excuse me, a farad is a coulomb per volt. And the micro we can just keep. And what we get is 36.00, or excuse me, 36.0. That's 4 sig figs. That's, yeah, 36.0. So this gives me 36.0 micro coulombs. That's the total charge that leaves the battery. Now, if you look at the original circuit, that means Q0 is what leaves here, but then Q0 is broken apart for C2 and C3, but it comes back together as Q0 there. So Q0 is also equal to Q3, which equals 36.00 microcoulombs. So we got that. We're about time for class to be over. I'm going to go ahead and finish this problem and then kill the video, but we'll continue on. So we now have Q3 and the total Q that leaves the battery. Now, what we do know is that Q0, excuse me, I should be writing in blue again. We also know that Q0 is what breaks into Q2 plus Q3, or excuse me, Q2 plus Q1. So we do know that Q0, because of conservation of charge, part of it's going to go to C2 and part of it's going to go to C1. However, what goes to C2 and what goes to C1, when you add them together, they have to be Q0. So we do know that that's 36.00 microcoulombs. Now, the other thing we know is that C1 and C2 are in parallel. C1 and C2 are in parallel, and that implies V1 is equal to V2. So using our C equals Q over V, we can say that V1 is equal to V2, but that's going to become Q1 over C1 is equal to Q2 over C2, like that. And that actually allows us to compute that Q2 is actually equal to Q1 times C2 over C1. So I can plug that into the Q0 equals Q2 plus Q1 as follows. I can say 36.00 microcoulombs is equal to Q2 plus Q1, and Q2 is Q1 times C2, and we said C2 would be 8.00 microfarads, and we said C1 would be 4.00 microfarads, plus, that's all Q2 now, plus Q1. So 8 over 4 is actually equal to 2, and this is Q1, by the way. So now I can say that 36.00 microcoulombs is equal to 2Q1 plus Q1 is 3Q1. So Q1 obviously is 36 divided by 3, which would be 12.0, and that's an extra sig fig there, extra sig fig. No, actually, those are right. I shouldn't have put that there. Just ignore them. This comes out to 12.0 microcoulombs for Q1. So I now have Q1 as well. And then Q2, of course, is Q2 is equal to C2 over C1 times Q1. That's what we already found. Of course, we also found that C2 was 8.00 microfarads and C1 was 4.00 microfarads. Those two cancel out to just give you 2. And then this is 12.0 microcoulombs for Q1. So this is basically giving us that Q2 is equal to 24.0 microcoulombs. So we now have the charges on all the individual capacitances, and now all we need is the voltages. I'm going to call this part B, even though I didn't, strictly speaking, call it B before. And now we'll do part C. And part C is finding out the voltages. In general, voltage is equal to charge divided by capacitance. So I can immediately start with V1 is equal to Q1 over C1. And we already found out that Q1 was in fact equal to 12.0 microcoulombs. And then C1 was 4.00 microfarads. The micros cancel out. 12 divided by 4 is 3. So that gives me that V1 is equal to 3.00 volts. Notice V1 is actually in parallel with C2 with V2, so it should be the same, but we'll check that ourselves. V2, excuse me, V2 should be equal to Q2 over C2. Q2 we found was 24.0 microcoulombs, and C2 was 8.00 microcoulomb or microfarads, and 24 divided by 8 is in fact V2 equals 3.00 volts. So that confirms that V1 and V2 are exactly the same because C1 and C2 were in parallel. Now, notice it also should be, since the total voltage is 6 and we just jumped 3 from going from the left of C2 and C1 to the right of C2 and C1. So we were at 6 when we left the battery. We stayed at 6 till we got to the left side of C1 and C2. And then we got to the right side, we had dropped 3. So now it's 3 volts on the right-hand side of C2 and C1, which is the left-hand side of C3. And then, of course, it's supposed to be 0. So we expect voltage across C3 to be 3 volts. And now we'll check. If it's right, then that'll be confirmation that we did it probably correctly. So this is part C. This is part C. And now we're going to say V3. Oops, I'm supposed to be writing in blue. We're going to say V3 is equal to Q3 over C3. Q3 we found was 36.00 microcoulombs, and C3 we found was 12.00 microfarads. 36 divided by 12 is 3, so 3.00 volts is C3, or excuse me, V3, and that's exactly what we had expected. So that's a way you can actually, in a higgledy-piggledy sort of way, that's a way you can actually solve a capacitance circuit. What you're supposed to do, of course, is work out the equivalent capacitance, and then using the equivalent capacitance, that'll tell you what charge leaves the battery. Then you might be able to find that that charge happens to correspond to the charge across a particular capacitor. That could be a capacitor that's directly in series with the battery on the negative side, or directly in series with the battery on the positive side. But if you don't have one like that, then yeah, the Q0 is not going to be the charge for any capacitance. But the Q0 is going to be broken up to some capacitances that are in parallel, and conservation of charge would dictate that the Q0 would be equal to the sum of the Qs leaving that particular junction. So you do that. Once you find the Qs on the individual charges, on the individual capacitors, then you can go back and also use C equals Q over phi to find out the voltages on all of them. So that's what we did there. Hopefully, y'all were able to follow that to some extent, and it's very much like one of the examples the book did. The book did example 24-5, but it used different capacitances. I think it used the same actual shape. I mean, I think the circuits were identical, except that I used 3 different capacitances, and the capacitance in the book used 3 that were identical. So I'm just going to say this is like 24-5. So hopefully that's it. Well, thanks for coming. Those of you that didn't come anyways, have a good day, and I will see you next time. Remember, you guys have a test. Good luck, and y'all have until Sunday of next week to get your test done. Make sure you sign up with a proctor, follow all the rules, all that good stuff, and have a good day. Bye, everybody. Oh, I said to end share and it went away. Oh, there. So, bye-bye.